All right, let's dive right into this explainer. Today, we're popping the hood to see exactly how engineers take a standard commercial truck and transform it into a highly specialized, high stakes emergency organism. When we see a fire truck racing down the street, it's super easy to just see a big red box covered in flashing lights. But the reality? A standard commercial chassis absolutely cannot handle the extreme thermal events these vehicles run into without some severe, highly calculated modifications. So, we are going to tear down the basic truck today and build it back up into a literal life-saving machine. To do that, we're basically going to assemble this beast from the ground up. We'll start with the anatomy of a fire truck, move on to the heart of the machine, look at taming the liquid beast, matching the truck to the threat, and wrap up with industrial versus municipal battlegrounds. Let's get right to it. Okay, part 1, the anatomy of a fire truck, starting with its engineered skeleton. So, think about this for a second. A standard commercial truck engine is designed to do one main thing: turn the wheels. But an emergency vehicle needs that massive diesel muscle to also drive a super high-volume water pump. How do they do it? Through the power takeoff, or PTO. The PTO is this absolutely critical mechanical bridge. It grabs the kinetic energy from the engine and transfers it straight to the pump. And what's really cool is that it ensures that even if the engine RPMs are fluctuating, you still get a consistent, uninterrupted flow of water blasting out of those hoses. It is literally the core of the truck's dual identity. Now, you absolutely cannot just strap a rigid water tank to a standard delivery truck frame and call it a day. Why? Well, commercial chassis are actually designed to flex and twist on purpose to absorb road impacts. But a fire truck carries this highly rigid tank superstructure. If you were to just bolt that stiff tank to a twisting frame, the whole thing would crack like an egg the second you hit a pothole. So, engineers solve this by installing floating subframes and spring-loaded brackets. This setup completely isolates the tank, absorbing the dynamic shock and letting the chassis flex underneath without tearing the water tank apart. It's a brilliant fix. Moving right along to section 2, the heart of the machine, which is the centrifugal fire pump. Older pump styles used to just push water mechanically, but modern centrifugal designs are way smarter. They actually utilize the incoming pressure right from the city hydrant. It's a linear progression of kinetic energy. Step 1, that pressurized water enters a specialized casing called the volute. Step 2, a rapidly spinning impeller grabs that water and violently accelerates it outward. And by step 3, all of that kinetic movement simply converts directly into massive discharge pressure. The result? A sustained, high-volume flow that firefighters desperately need. But wait, all that intense kinetic energy, it brings a pretty serious operational hazard. Imagine a firefighter on the hose line suddenly snapping their nozzle shut. Because it's a centrifugal design, the impeller can actually just churn the water inside the pump safely for a brief moment. That's a lifesaver, really, because it prevents the plumbing system from just blowing apart. However, leaving it churning like that for too long is bad news. That continuous friction causes internal cavitation, and it will literally cook the pump from the inside out, leading to severe thermal damage. Which brings us to section 3, taming the liquid beast. We're talking payload and physics here. Imagine hauling thousands of liters of liquid at high speeds. It creates a massive kinetic hazard. When a heavy apparatus slams on the brakes, that moving mass of water transfers all its kinetic energy straight to the front axle. A sudden surge during a hard turn, that could easily induce a catastrophic rollover. Which begs the question, a literal life or death engineering question, really. Why doesn't a speeding fire truck just flip right over when it takes a corner? Well, the secret is actually hiding right inside the tank. They're called internal baffles. Engineers weld these rigid transverse and longitudinal walls directly inside the holding tank. Now, they aren't solid walls. They have these small, precisely calculated flow openings. This setup allows the weight to distribute evenly, but more importantly, it disrupts the violent momentum of that shifting liquid. It's an internal stabilization system. If these baffles were to fail over time, that kinetic liquid surge would literally destroy the chassis alignment. And speaking of the tanks, what are they actually made of? We're seeing a fascinating shift in the industry right now. Traditionally, you had carbon steel. Great rigidity, sure, but it is heavy and demands constant, continuous anti-corrosion treatments. Water and steel just don't mix well long-term. Enter polypropylene. Modern engineering teams, especially those building for salty coastal environments, are moving to these synthetic tanks. Polypropylene completely eliminates rust, it resists harsh chemical degradation, and it drastically drops the curb weight of the truck. And in this business, less truck weight means you can maximize the total water payload the chassis can legally carry. All right, section 4, matching the truck to the threat. let's look at the matrix of apparatus. Because, let's face it, a one-size-fits-all approach is absolutely useless in an emergency response. When we look at global manufacturing, specifically Chinese OEMs, we see them engineering 4 highly distinct setups to counter specific threats. You've got your standard water tankers for Class A structural fires. Then, foam tenders designed to smother Class B petrochemical vapors. Next are the rescue tool trucks, which actually skip the heavy liquid payloads altogether so they can carry complex hydraulic and pneumatic tools for extractions. And lastly, aerial platform trucks, equipped with massive, hydraulically stabilized booms for high-rise structural events. If you map the specific tool to its exact hazard, the differences in capacity are wild. A water tanker dealing with Class A combustibles holds anywhere from 3,000 to 10,000 liters, but a foam tender facing a Class B flammables fire, it needs a massive volume to create that thick chemical blanket, sometimes pushing up to 16,000 liters depending on the axles. Meanwhile, the rescue and aerial platforms don't even carry their own massive liquid payloads, since their mission is purely about structural access and equipment relay. Now, if you're dealing with one of those Class B petrochemical fires, just dumping regular water on it is an instant fail. Engineers have to figure out how to inject precise chemical mixtures directly into the hose line. And they do this using 2 main foam proportioning systems. First, you have Venturi-style inductors. These are super reliable, low-maintenance mechanical setups that basically use the water's own velocity to create a vacuum and suck the foam in. On the flip side, for massive industrial incidents, you need balanced pressure proportioners. These actually use a secondary positive displacement pump, which lets operators dynamically tweak the foam percentages across multiple independent hose lines on the fly. And finally, Section 5, Industrial versus Municipal Battlegrounds. The environment these trucks operate in literally dictates everything about their design. Municipal environments have really strict dimensional constraints. If you're in a city, you need medium-duty platforms with tight turning radii and rapid acceleration to navigate paved avenues quickly. But industrial facilities, places like oil refineries, those fires grow incredibly fast and burn insanely hot. Those giants require heavy-duty chassis structures. The radiant heat is so lethal at a chemical plant that manual hose deployment is pretty much impossible. Because of that, automated, remote-controlled foam deck monitors are strictly mandatory for those industrial trucks. So what happens when you start exporting these specific trucks globally? Well, fleet managers basically have to solve a massive logistical puzzle. A standard 4x2 urban pumper is going to be totally useless stuck in rural, unstable soil. Topography dictates you might need a 4x4 or 6x6 configuration just to maintain traction. Then there's emissions. If a region has inconsistent diesel refinement, you have to run Euro 3 engines. But a modern urban center, they require Euro 6 platforms with complex particulate filters. If you miss even one of these details in the blueprints, you risk catastrophic vehicle immobilization when it matters most. Of course, with the stakes being this high, all this intense engineering is locked down by super strict global frameworks. We're talking standards like the NFPA 1901, the European EN 1846, or just baseline ISO 9001 quality management. These groups rigorously review everything. They make sure the chassis layout, the PTO flow, and those internal tank baffles all integrate perfectly. That way, when the alarm finally sounds, the machine performs absolutely flawlessly. So let's bring it all together. Think about the incredible, unseen engineering we've unpacked today. You've got those hidden rigid baffles fighting back the liquid momentum, the centrifugal impeller converting raw kinetic energy, and those floating subframes quietly absorbing the shock of the road. The next time you hear a siren screaming down your street, I want you to ask yourself, do you just see a big red truck? Or do you see a dynamic, highly specialized mechanical organism roaring right beneath the surface? Thanks for hanging out with me on this explainer. I'll catch you on the next one.